Thank you everyone for joining us today. So it's another ASEG webinar series. We're also hosting this one live in Adelaide with the audience we've got here. So today we're lucky enough to have Dr. Anandaroop from Geoscience Australia, who's going to be talking about learning to learn the Earth about using Bayesian inference. Before I start, I've just got some housekeeping slides I just want to bring to your attention. So none of this would be possible without our sponsors. This is the Corporate and the Corporate Plus, and who also support the ASEG Research Foundation, which supports the honours, masters, and PhD students in geophysics. So there for the corporate, we got Southern Geoscience Consultants, Transparent Earth Geophysics, Santos, and Down Under Geoscience. And our Corporate Plus sponsors are High Size, Total Seismic, and Geoscience. And we've also got the local state branch sponsors. We've got New South Wales, WA, and finally SANT sponsors, who without them wouldn't make it possible to hold these events in each state. Just a bit of housekeeping here. So if you have any questions, there's the Q&A panel. Feel free to type it out through there as we go along. And try not to use the chat box, but we'll try and monitor both of them. So I'm pretty sure there'll be plenty of time at the end for a Q&A as well. Just a few upcoming webinars. On Wednesday 21st, we've got Dr. Vivek Harish Loda, who's going to be talking about shallow mantle convection between West Africa and source to sink continental margins. This is a novel approach to reservoir prediction in offshore deep water settings. And we've also got a local SA branch event coming up, the Fall Fleet. It's a great networking event, which is with the PISA, SPE, and YPP. And just a quick thing, a few member benefits. So you get the free access to the technical journal Exploration Geophysics. You got the free copy of the preview, reduced entry to the AEGC conferences. We got the one coming up in September in Brisbane, and also annual wine offer and lots of other goodies there as well. And if you want to keep in touch, you can hear us, talk to us through LinkedIn, Facebook, Twitter, YouTube as well, with all the webinars on there. Share screen. There we are. Cool. So today, like I said before, we got Anandaroop from Geoscience Australia. So Anand started his career as a non-seismic geophysicist who worked with shell exploration and production in 2007. In 2010, he joined the PhD program in marine electromagnetics at the Scripps Institute in San Diego, California. And in 2014, he completed his thesis, focusing on uncertainty estimation in electromagnetic inversion for marine hydrocarbons exploration. From 2012 to 19, he worked for Chevron R&D, where he was doing working on various R&D problems in CSEM, seismic full wavelength inversion, reservoir properties from seismic, AEM, statistical hydrocarbon exploration, and the role of machine learning in geophysics. So the question from his work was, how critical can we interpret our inversion models? The answer in which often requires the use of the high-powered computers. In 2019, he joined the Minerals, Energy and Groundwater Division at GA, where he continues to work on inverse uncertainty, model representation, and geostatistics. And lastly, Anand has just had a paper accepted in the Geophysical Journal International on Bayesian inversion using nested transdimensional Gaussian processes. I'll give it up to Anand now. Thank you.
Thank you, Ben. And how do I know that people are actually able to listen to all of these things? Because is there a mic check or something we can do? Or?
That should be all good. So we got the. So.
Okay, so
yeah.
it looks good. So if it isn't, just yeah, someone just pop up and send us a message.
Yeah.
Okay. Cool. Thank you very much, Ben. Yeah, there's quite a few mouthfuls in there, and yes, the title of today's talk, which is "Learning to Learn." When I tried submitting this to Geophysical Journal International, it got rejected immediately because the editor said, "Well, there's a typo in your title," but there actually isn't. This is actually about learning to learn, and so I'm going to talk about that. It is a little bit nested and recursive, and so the first time I showed this to people, they thought I was crazy. So I really thank the individuals noted underneath for their zeal and enthusiasm, because if you don't have some of these things, you're not going to have any patience with me trying to explain nested algorithms. But as a consequence of their efforts, hopefully it'll be much easier for the rest of you, and I've provided a distilled view on how we can do Bayesian inference, and also be honest about the things that we don't know. So we have two levels of Bayesian inference. So while that might sound very abstract, let's just begin from the beginning. So the Bayesian point of view, when you're solving an inverse problem, it's just what you see on the screen. You start from the right, you've got a bunch of, let me get the fancy pointer options, laser pointer. You've got a bunch of prior beliefs, and then you draw from these prior beliefs. You examine what you draw by putting it through some physics. That gives you some calculated data. You hold it up against the observed data, and then you compute a misfit. And usually we appeal to stacking, which implies central limiting, which implies Gaussianity. And then we convert that misfit by just saying e to the minus of that misfit gives you a probability. And so we combine our prior belief, we combine the probability of that misfit to give you an updated belief. And then using various kinds of techniques, we do this over and over and over again until we get an ensemble of models. And so it's basically this equation, which I've stated in words. You start from your prior knowledge, you look at the accuracy of the predictions for your likelihood, and then you get this updated belief in your model. And that's really all there is to it. It's not very much more complicated than that. So we live in a Bayesian world. We form notions about the world. Then we, talk to people. We interact with people. We interact with our surroundings, and then we adjust our notions about the world based on our interactions. And so then we have an updated belief. So it's really no more complicated than that. So a lot of you might have heard of transdimensional Bayesian inversion. Maybe you haven't, but that's okay. Most of you have heard of Markov chain Monte Carlo. So it's a way to sample a model space. If you've got, say, 10 parameters in the Earth, you've divided the Earth into 10 layers, you want to find the velocities, the seismic velocities, if you're doing a tomography problem, in each layer. If you're doing a magnetotelluric problem, you want to find the resistivities in each of the 10 layers. So that's ordinary Markov chain Monte Carlo. So it's the probabilistic analog of your deterministic inversion methods like, Occam or Gauss-Newton or any of these. So a statistician called Peter Green back in 1995 introduced this method called the reversible jump, or the transdimensional method, which was picked up by Alberto Malinverno, who's at Lamont Doherty, and was also popularized by Malcolm Sambridge et al. In the geophysics community, where the number of things you don't know is also an unknown for the problem. So if you want to find out about velocities in the Earth, you also need to find out about the number of velocities in the Earth. And so, so you kind of extend this to an unknown number of unknowns. And so if you've got k unknowns, if you've got k velocities in the Earth, these fractions f1, f2, fk represent products of how much of that prior space you're occupying. So if in the first layer you occupy 10% of, say you thought your prior range of velocities was, from 2,000 meters per second to 6,000 meters per second, after you've performed your experiment, it's not going to be that large of a range. It's going to be some fraction. So in the second layer, you're also going to have a similar fraction. In the third layer and the kth layer, you're going to have a fraction. Always, that fraction is going to be less than 1. So what you get is this product of fractions. And so that very quickly tails off the more number of parameters you have. But this term over here, this data given a k parameter model vector, is the probability of fit. So the more parameters you add, the better the fit gets. So this automatically falls out of Bayes' theorem, where you've got this term which falls off to 0 as you add more terms k, and you've got this term over here, which is the likelihood of your fit, which, as we know, gets better as you add more and more parameters. So you've got this balancing which occurs in transdimensional problems, which is really nice. You don't have to say, I am now going to regularize using this philosophy or that, or it's intrinsically built into Bayes' theorem, this idea of regularization. Though this annoys everybody, I've never found a better way to explain this, because the Bayesians tell me that it's not regularization, and the determinists tell me that I'm not regularizing enough. So yeah, so anyway, so I think that that's how it works. This is an intrinsic way of doing regularization, and it upsets both the Bayesians as well as the determinists, because it does a little bit of both together. Now, I came across, so I've been trying to learn, as Ben said, about machine learning, because everybody's all about machine learning. It'll solve all your problems, world peace. So I tried very systematically and slowly trying to understand these methods, as opposed to trying to use them, because it's very easy these days with scikit-learn and with all of these methods to just apply your methods and get a result. And it looks like nothing you've ever seen before. And oh my God, isn't this exciting? Maybe. So I tend to be a little slower with these things. So I started with what's been studied in geophysics a long time by the name of kriging. In fact, it was Krige who at the University of Witwatersrand in South Africa, I think in the 1950s, invented this idea where you sample a bunch of points and then you want to find out what's happening in between those points. And the machine learning people call this Gaussian process machine learning. It's really as simple as that. So if you've got a function with some values between 0 and 2 on this axis, and it extends in some domain between 0 and 0.4 on this axis, then the true function is given by this dashed black line. And I can sample it at a few points, these magenta points. And then on the basis of what I've sampled, and my giving the Gaussian process a length scale, which in this case was half a box width. So if that's 0.1, that's 0.05. I just said use a length scale of 0.05 and interpolate everywhere else. And so you see these blue lines, or you see a blue line that forms as a consequence. So I thought, well, this is interesting. This is kriging. We also know that you can do trans-D, where you can add and delete the number of parameters in your inverse problem. So could we put the two together? So, well, if you think about it, you should be able to, right? Because instead of 10 points, if I've got 15 points now, well, I get a much better approximation to my true function. And you'll say, well, this is nice, but we're earth scientists and you're just a pretend statistician and all of these are true. Then why should we do this? Well, the reason we can think about doing this is we can move away from this paradigm of layers in 1D, Voronoi cells in 2D, something else in 3D, because with the same formulation, you can do 2D and 3D modeling using the same mathematics, because these nuclei, or these little magenta points in this case, or the black points in this case, or these little nuclei you see over here can represent a 1D function, can represent an approximation to a milk drop. That's what you're seeing over here. That's an image which basically represents the pixel values of a drop of milk. and I can do that using these little dots in the background. So I think there's 40 of them. Or I can represent three-dimensional structure, as you see over here, for a moderately shallow mental type problem where you're going down to about 500 kilometers depth. I can parameterize something which looks like resistivity using just 40 or 50 cells. And this is very useful because a lot of what regularization or trans-D or these methods of keeping your model stable in geophysics, what they need to do is they need to keep the number of parameters you're interested in small. And so, and that's cool, because if you look here, there's actually, I think, 100 grid cells that you don't see on this axis, but I've been able to populate it using only 15 points. This image is actually 256 by 256, which I think is 65,536. But don't quote me on that. But you can populate this entire image, which is still a model vector with only 50 points. You can do something similar for this, I think, 32,000 cell model that you have over here with 50 points. And if I didn't tell you that this wasn't from an empty problem, you'd begin to interpret structure there. Sorry, I shouldn't be saying that. But point is, there are statistics everywhere, and we should be having statistics that's like our data. So actually, there's nothing wrong with drawing lines on that. You just need to know where that came from. So all of this is possible with a Gaussian process mean, and I promise you there's only like 3 slides of equations in this entire talk. So it's, less than a seventh. So here's your 1D function, and this blue line I constructed using this equation, and the blue line is what I'm going to call mu star, and it's the large model vector. It's the one that's across 100-dimensional grid cells. And then you use these kernel matrices. There's a cross kernel, so that's in between all of the 100-dimensional grid points on this axis with the 15 points across this. So that's, this matrix over here. Then there's a self matrix, which is 15 by 15. But ultimately, what it does is it gives you a way to go from 100 by 1 to just 15, because it's just matrix multiplication. So I can now keep track of just 15 things to control 100 things. And so if you think about it, it's really like, in the days when we used Photoshop or PaintShop Pro, and you wanted to change something, a line, you just do it in PowerPoint, right? When you're making Bezier curves, you're moving these points. That's exactly what this is. You're just moving these nodes, and you're using Gaussian processes to do it. And what you need to provide the Gaussian process is an idea of similarity. So if you look at close to the magenta points, the blue line is always very close to what the values in the magenta points are. But when you get further away, the values depart. So you've got to provide a similarity length. Or in geostatistics lingo, I think it's known as a range. I think that's what the geostatistics people call it. And so you've got to provide a correlation length. And so once you provide a correlation length, that tells you something about your function. So it says, even if I'm yay far away from any observed points, just model it, trying to keep it similar to what you've seen using this length scale. So things that are far away from that similarity, further away from an observed point on the similarity length, will begin to then look less like the points that you've seen. And that makes sense. So you have a notion of closeness and distance that is built into this methodology. And again, what does this have to do with geophysics? What if I rotated the Earth? What if I rotated the diagram that I showed you before? And now you could think of this as being Z in the Earth, and you could think of this as being some property, take your pick, conductivity, velocity, thermal conductivity for the likes of Derek over here, who likes to play with heat flow and heat production, the difference between which I've been learning only in the last week, so shame on me. So yes, you can actually use this for a geophysical problem, because look at that. This is actually helicopter AEM data, and I'm not going to tell you where, but yeah, so this is a whole ensemble of resistivity models and sorry, my geophysical training has largely been in the US. So I think in terms of resistivity, everybody in Australia, it seems, likes to think about conductivity. But for you, I have flipped the axes. So it is conductivity increasing as you go, right? And so there's a very briny conducting channel over here. And you can kind of figure out from the ranges of resistivities we're looking at over here that, well, this has got to be ice, right? Because this is 10 to the 6 ohm meter. So it's like super resistive stuff with like a briny channel in between. There's only that many places in the earth where this can happen. But because we're still trying to write this up and I haven't, so I'm just going to leave it at that. But you see the transient model responses for helicopter AEM, and it fits the data. So yeah, so this idea of using Gaussian processes for doing geophysical inversion is entirely possible. So in this case, I haven't shown you the little magenta dots because there'd be too many of them, because I've shown you some random ensemble of 100 models. So I'd have 100 sets of magenta dots. So I've spared you the visual clutter. But yeah, so you can use this mechanism to parameterize the Earth and also solve an inverse problem. And then you'll say, well, you've been doing this in 2D, in 1D, and how about getting to 2D? And as I said, this method is dimension agnostic because a model vector is a model vector. It's 50 nuclei can exist in 1D space, can exist in 2D space, can exist in 3D space. And this is actually the uncertainty that's been imaged around the Gemini prospect in the Gulf of Mexico. This is from Carrie Key's thesis, but we just reworked the data using these Gaussian processes. And our student and now our colleague, Dr. Dan Blatter, who's now at Scripps, has recently published this. That's very timely. Let's get on with it. So Dr. Dan Blatter has published this in Geophysical Journal International, and you can clearly kind of see just the salt body and overhangs. And this is marine MT. And never believe anything that someone shows you that's a nice image unless you can look at the data fits. So just to not be a hypocrite, I've provided the data fits over here. As you can see, this is very different from land MT because the periods you're using are quite large. This is quite low frequency. We're only going from 1 second to about 100 seconds over here. And yeah, there's some 7 sites. That's apparent resistivity and phase. But yeah, it fits the data. So I'm not just showing you pretty pictures. But then the question arises, everything you've shown so far, Gaussian processes, kriging, it's all smooth. So what happens if you've got discontinuities in the data? And this is a horrible function if you had to fit it with any kind of geophysical method, because it's both smooth and sharp. And so how are you supposed to represent this? And actually, my partner, who's a neuroscientist, neuropsychologist, she saw this and says, this looks like activation potential in the brain. And actually, that's where this is sourced from. So all of these statisticians were studying activation potential for neurons in the brain, and they've been doing this for a while. And so they've actually been trying to fit functions like this for a while. So there's a lot of literature. We don't have to reinvent the wheel. We just have to look elsewhere. And there's good stuff there. So you can use the ideas that I just mentioned, the transdimensional Gaussian processes, the same ideas that have been used to infer the briny channels in the Antarctic ice. So you can use that same machinery to do a probabilistic regression problem. And look at that. It's able to, with a fixed length scale, which in this case was 0.1 units, I think, able to fit the discontinuity quite well. And this is because of the flexibility of these transity methods. You can add or subtract the number of cells, and you can change their location. So I was quite surprised that it was able to do this. However, this is the data noise level, and negative log likelihood is just a fancy way of saying half of the chi-square misfit. So maybe I should just say half of the chi-square misfit. It's just the misfit. This is because it's a synthetic problem, and also because I know something about the noise. This is where it ought to have gotten to. And I'm running a whole bunch of Markov chains in parallel. So each iteration of a Markov chain corresponds to a model. And in this case, I've got 1, 2, 3, and there's one hidden in the background you can't see. So 4 models that are running in parallel, all of which are running all the time, exchanging information with each other to give you inference in this black chain, which is your the target chain for doing inference. And when I pull out the ensemble of models in this black Markov chain, I'll be able to plot statistics like I've done over here. But it doesn't quite fit the data within the noise. And so that's a little bit problematic. And why is that? Well, we know that it's because of the sharp edge. So what we can do differently is we can use nested trans-dimensional Gaussian processes. And I swear, this is the last slide of equations. What you do now is that at every location in the Earth, you assign a length scale. And so then what you can do is the kernel function, which I was using earlier for creaking, that is now no longer stationary. That kernel changes. So that allows for the length scales in your model domain to change with space. And you'll notice here that if I equals to j, then these 1/4, 1/4, and half terms just cancel out, and you're back to life as usual. So it's a very clever modification that the statisticians that I pointed out on the previous pages have worked out, and you can read more about it in detail in this paper that Ben was talking about, this latest paper that we've published. Yeah, and so what we've got there is what's known as a 2-layer Gaussian process. So it looks a little bit complicated, but essentially you've got 2 Gaussian process means. One is stationary and one is non-stationary. This non-stationary guy here is the one that contains the resistivities that we need to put into, say, a controlled source electromagnetic modeling engine or an MT modeling engine, or if you were doing seismic tomography, your Iconode solver. This guy over here is actually a model that parameterizes the length scales of your velocities or your resistivities. And so your finite difference engine, you don't provide it length scales. You have to provide it, the resistivities, or you have to provide it the velocities. But to compute the velocities or the resistivities, you need the length scales. And so they're kind of intertwined with each other. So it's badly explained in these figures. It is a little bit complicated, but what you're doing is you're doing inference twice. You're doing inference on the properties, and then you're doing inference on the properties of the properties. But your finite difference, your finite element algorithm doesn't care about the properties of the properties. But the properties get modified when you're changing the properties of the properties. So you've got a bubble from the way all the way down, back up, and that's kind of why it's a nested inference. It becomes clearer if you look at this image over here. So now I've added a second trans-dimensional Gaussian process, which parameterizes the length scales of this image that I'm trying to fit over here, or the function that I'm trying to fit over here. And very nicely, using the same theory that I would have used in when I wasn't using 2 of these together, but it's just that I've done the same thing twice. The second level trans-dimensional Gaussian process is able to figure out that at about 0.4, there is a sharp drop in the length scales. And that's right, because that's exactly where you've got this very sharp change. And so, points over here are not very correlated with points over there. So that length scale, that correlation length is very small. So it's nice because the algorithm's able to self-parameterize. And if you think about it, if I just fixed the length scales here, I'd be assuming some knowledge of the length scales in my problem. But often in the Earth, we don't know what the length scales in the Earth are. The Earth is, does exist at multiple resolutions, and geophysical resolution changes with depth. So there's all these reasons to add this complexity. And if you're not convinced, I'm going to zoom in. When you use only a stationary Gaussian process, trans-dimensional Gaussian process, and when you use a non-stationary one. So at the location of the jump, what you're seeing is that the true value, which is given by these dashed lines, and the data points are given by these white circles over there. The inference, where darker colors correspond to higher probabilities, or sorry, the other way around, the lighter colors correspond to higher probabilities. The high probability areas are actually able to encompass the data as well as be closer to the true value than in the stationary case. And well, this happens because if you zoom into the length scales also become shorter at about 0.4 when you use the non-stationary formulation. And so this proves that if you have a second level of inference, it can actually self-parameterize to figure out things about itself. And so in this day and age of machine learning, et cetera, it shouldn't be surprising because you use these algorithms, you throw lots of data at it, and out it comes with ears and noses and, you know, mouths, et cetera. These algorithms are learning to self-parameterize. And I'm not claiming this is machine learning, but the idea is the same. So you start out with these generic algorithms, which you keep using, such that they're able to figure out from the data, if the data are informative enough, how to parameterize themselves. So I think images are, you know, useful to kind of explain this kind of thing. So again, there's my favorite milk graph image. That's 65,000 pixels because it's 256 by 256. I give it something like 2% of the data, and I want to reconstruct the original image. And I can do that using a fixed length scale. And this is not a bad approximation. But you can kind of see that this is speckly. The effects of the length scale are very evident. You know that I've used a length scale, which is roughly the diameter of any of these speckles. Now, if I used a non-stationary transdimensional Gaussian process, where the length scales aren't fixed and I'm inverting for the length scales as well, voila. So for those of you who aren't convinced, and the reviewers were like, yes, we can see this, but give us numbers. So we give them numbers. This is something called the peak signal to noise ratio, which you can compute when you're looking at compressions of images and the fidelity of your compression, and higher values are better. So you're actually, you know, doing 2 dB higher than you were doing for the stationary figure. So you're definitely doing better in figure D, that's over there, than you are doing over here. So your eyes aren't lying to you, as in this definitely is a better approximation to this than this is. However, both fit the data. So there's nothing wrong with this, but this is a better representation. You can also slice through the uncertainty, and this provides some interesting ideas. So I've got the median image from the regression, and I've taken a slice through it, and you can see the uncertainties in your slice. So I've got the P5 and P95 quantiles at every location, and lighter colors are more probable. And, you know, you can see that generally uncertainties are quite low in your pixel values. And if this were a 2D problem, this could be conductivity, velocity, whatever you like. Those are the only two I know, so pardon my imagination. And you can also go through the X, the inferred length scales in the X direction. And this is the median value of the length scales in the X direction. And I can take a slice through it. And note that when I'm going from there to there, there's a sharp change about there. Well, it's not the sharpest of changes, but you can see that the length scales must change. And so that's what you see here. The length scales are dipping. And then when you are within this drop of milk, when you're here, the length scales remain more or less the same. And then again, the length scales are dropping. And that's what you see over there. And it's harder to explain the why, so I'm not going to, but you can look up our paper. But generally, this is very in tune with our ideas of how, you can think of this actually as the Fourier transform, though it's not the Fourier basis, where you'd expect to see sharp harmonics at certain locations, but you can kind of localize those changes over here. So more like the wavelet transform, but I'll stop going off script. you can use the same idea to invert real geophysical data. And this is an Australian example. This work was part of David Meyer's PhD thesis. And then we had a go at it in 2014 as well. So the rabbit ears, as Dave likes to call them, is where all the good stuff is happening. This is a gas reservoir at about 1.9 kilometers depth. And I think this is the 50% gas saturation line that's been inferred from seismic studies. What makes this a particularly challenging target? So for those who may not be familiar with controlled source electromagnetics, it's sensitive to resistors, unlike MT, which is primarily a TE mode thing. CSEM, at least in the pure 1D world, has a TM mode thing. So it's actually got currents that go vertically into the earth. So it's very good for figuring out resistors. But as luck would have it, we've got these girly siltstones from about 1.6 kilometers underneath sea level, all the way down to the reservoir level, actually. So it's an interbedded laminated reservoir. And I've just provided a blocky diagram over here. So you've got the girly siltstones, and you've got this resistive reservoir, which is not a whopping resistor. It's just about 14 ohm meters or something. So it's not super resistive. So you've got the girly siltstones, you've got the reservoir. So using deterministic inversion methods, it was really difficult to tease out the reservoir unless you basically knew where the reservoir was. And so what we were able to do using transdimensional Gaussian processes is model that horrible geological setup in the on-reservoir area. And you can see that both around where you expect to see the girly siltstones and around the reservoir, you've got these sharp peaks. And you can kind of infer that there is a reservoir there, and you're able to fit the data because the blurry black dots are the real and imaginary radial electric field at 4 frequencies. So you can fit the data. The colors represent the observed data. You can fit the data quite well. However, when you use a non-stationary formulation, just look at what happens at 2 kilometers depth and look at what happens above. So, you know, if you had to pick a reservoir using this versus this, you probably would go with that, right? And they're both able to fit the data relatively similarly. The only difference between the two is that one uses this idea of inverting for the length scales as well. So I'm not fixing the length scales in the inversion. I'm not picking the smoothest length scale as you'd do in Occam, which is not a bad idea. But what I'm saying is that there's more information in the data that you are able to tease out if you parameterize the problem with the second level of inference. And this shouldn't be surprising to us in this day and age. Just look at the algorithms around you, which we're using on Google and Facebook and all of those things. Zooming in, this is, you know, so what you would get from the blocky model, this white line that's on both the stationary and the non-stationary images. I'm going to draw your attention to the probable parts, which are you know, in the heat map are light colors. And what you're able to see when you use a stationary Gaussian process, where I was trying to keep the length scale small so as to be able to figure out sharp, subtle changes, I was only able to capture the bottom of the reservoir. And that's because in the Northwest Australian shelf, my colleagues at Chevron told me that they've got these sequences which are fining downwards. So you've got these interbedded silts and sandstones, and you've got the reservoir. However, what that means is that there's not a sharp contrast at the top. And you've got to go down until there's a sharp contrast when you're going from the reservoir back to the sands. But above, it's this fining downward sequence. So these alternating sand, shale, silt sequences interplaying with the sensitivity of your method, when you allow the algorithm to self-parameterize, it says, look, I can't pick for you exactly where the reservoir is. And again, this white line is just a blocky approximation. But it's saying that there is a broad change in bulk conductivity, and there is a sharp change around there, which I can infer for you. And so it's basically able to capture the fining downward sequence and the sharp change, whereas this is only able to capture the sharp change from the finding downward sequence. And if you hadn't known about finding downwards over here from other data, you might not have been able to infer a reservoir. So this is a difficult target, but I'm just very happy with the way that we're doing with a difficult target over here. So to conclude, transdimensional Gaussian processes, they're quite generic. You can use them for various kinds of inversion problems in 1D, 2D, and 3D. You can nest them, so you can use two levels of inference when you know that the properties you're trying to model are non-stationary. And to sum it all up, to learn about the Earth, we must learn a little more about the Earth. And then you've got to propagate this back up. So you can think of this as the factorial function. So, like, what is the factorial of 3? Well, it's 3 times the factorial of 2. And so, you do that once and you do that again. Or another way of thinking about it is like a Taylor expansion. You've got the first level of the Taylor expansion, which is your constant term. The next term is your derivative term. The next term is your second derivative term. And then, it turtles all the way down. You've got to end it somewhere. And it seems that ending it at 2 levels is reasonable. So we've got a 2-layer Gaussian process in our work over here. And you can read all about it. And thank you for your time.
Thank you, Anand. So any questions in the audience here? Let's check the Q&A on.
No, I completely lost the audience.
Can't see any questions on the Q&A. Let's check the chat.
Did you try nesting it 3 times?
No, I didn't, because I think at some point in time, you've got to call it. Is there a good quantitative way to do it? I don't know. I really don't, because I'm really against complicating things beyond what they ought to be. And the entire idea of transdimensional methods is using parsimony. So you try to use as few parameters as possible. So technically, you could do trans D to figure out the number of layers as well. But that's the nice thing about these algorithms, is that the theory and the code is generic. You can just apply the algorithm to itself to figure out like how many levels it should be. But I didn't do that, no.
So we got a question from David Annette. Could you comment about the runtimes?
Very, very perceptive question. Yes, indeed. So if I'm running 2 transdimensional processes, so the way I've got it working now, you've got twice the cost, because you've got to propagate the changes up once. That'll change so say you've got a length scale and you change the length scale, it'll now change the velocities or your conductivities, and you've got to propagate that through your finite difference modeler or your 1D reflectivity modeler, or whatever you might have. So that's one step. And then the next step, you've got to do updating of the velocities themselves. And so it's twice the computational cost. But I would argue that for problems like magnetotellurics or seismic tomography, where you know that the length scales of the Earth, as well as the resolution with which you can infer the Earth, are changing with depth, it is well worth the effort because of the differences in the posterior inference. You just get a better result. But yes, you do have to spend the time on it.
It's not just that the length scales change with depth, then it's also that the length scales change as a function of the conductivity above it, right?
Yes.
So
Yes, absolutely right. Yes. And we don't know that conductivity a priori. So it would be good for the algorithm to self-parameterize. Very good point. Yes.
So we got another question from Alexei Gorbatov. What's the difference with the nested trees of the RISE method?
Oh, so Rees-Hawkins has similar methods as well, and they are also remarkable in that they are dimension agnostic. They work in 1D, 2D, and 3D. And Rees and Malcolm had this beautiful paper called Transdimensional Imaging Using Wavelet Trees from back in 2015. However, we've actually used this for seismic full waveform inversion, and we found that figuring out how to put a prior on these things in the wavelet domain is kind of hard. Because it's an abstract space, and I don't really have so much intuition for the wavelet domain. And so setting priors and prior bounds was quite hard. So instead we found that over here, I just have to set prior bounds on properties. I have to say that conductivity vary from nice 10 to the 6 ohm meters to, 1 over 10 to the, so 1 Siemens per meter or something, or 10 Siemens per meter if it's hypersaline. If I'm setting length properties or prior bounds on length scales, well, they're in meters, and I understand meters, and I know that. Or if I'm doing it for a problem that's in geochronology, that's in terms of time, I can say that the minimum time of change can be so many 100 years or so many millions of years. So the length scales and the properties are in domains that are familiar to you. They're not in the wavelet transform domain. So that's why I think that this is easy to use.
Cool. And we got a question from Kim Franco. In your slide showing the inferred length scale from the brain signal, there was an overshoot in the length after the chirp. That caused ringing in the prediction of the chirp. Any comment on why that exists and how you could compensate?
That's a really good point. So if you look back at that image, there is a bit of a chirp, and I suspect it's because. So if you're still able to see my screen, so you see a bit of ringing over here, and that's because of the placement of the data, because there's this noisy data point which is off from the true data, which is this white line over here, and you've got the noisy data point which is over there. And in order to, because we're not using any physics over here, right? We're saying that the noise is Gaussian, and so go figure it out. So it's just trying to accommodate that data point. And it's just, I suspect that it's just, the location of that data over there, which makes it like that, because it's clearly off of where it ought to be.
And just one last one here. In a nutshell, what would be the strength and the weaknesses of the TDG for multi-scale modeling?
I think it adds a lot of complexity. So if you look at these two, if you compare these two images, yes, if over here in one grid cell, you can approximate this sharp change, whereas over here, you need 3 to 4 grid cells to be able to approximate the change. But if you ask me, this is a pretty good approximation, but yeah, it isn't fitting the data quite. And this is a better approximation, and it is fitting the data. But in this case, I don't think the difference is that obvious. However, when you look at the image, this is much worse an approximation than this. And the only difference, which I probably could tune this to give me something like that, but it would be very manual. I'd have to run it a whole lot of times. Whereas over here, I'm just being upfront saying, I'm not trying to tune my image to get the best image. I know that it's within these ranges. So it's, I think, a more, I don't want to use the word honest, because it's not that we're being dishonest, but it's a more open-minded approach, saying I don't know everything there is to know, and the benefits are quite significant, because if I'm allowing it to self-parameterize over here, I will get a better result. And if you looked at the CSEM example, like, there's no doubt that this is a better approximation to what you're looking for than this. So the answer is, unfortunately, it depends.
Thanks for that answer. We'll probably wrap it up here. I'm pretty sure if you have any questions, feel free to contact Anand. His email address is up there.
No, it's not, but you can find me if you look for me. Yeah, it's
easy done. And just one last thing, just a thank you, Anand. There's a bit of the ASEG wine from last year. I hope you enjoyed that one.